All right, and I'm not sure, but we might be live, and I'm going to be checking right now.
Let's go.
Let's go.
Let's go.
Okay, as soon as it tells me I'm live, then I'm going to assume that we're live. But until it tells me explicitly in bite-sized words that I can understand.
Brian, if you don't full screen this,
yeah,
we're gonna have a problem.
I was actually thinking maybe if we just kind of shrink it a bit, and then it can fit on a phone.
Oh man, that would.
Just was thinking. Oh yeah, okay. Says it live. Hello everyone, and welcome to Tech Topical Tech's Best Talking Show. I am your host, Brian Ross, and today we have a very exciting special guest, a Tech Topical favorite. It is, of course, Chris from Stockton University, and Chris, I got some things I want to ask you about today.
All right.
Yeah, so here's what's going on here today. As always, folks, we are going to be watching a video, and I don't really know what's going on, and I'm hoping you kind of know what's going on, Chris. I'm hoping we can kind of figure out what's going on. So my mom might be watching, and we have to explain it simply enough for my mom to get.
Hello, Mrs. Brian's mom. It's been a long time.
And I'm sure she's saying hi back right now. But yeah. I don't know, dude. Hold on. Let me
My mom asked about you, by the way. Brian's mom. She asks about you all the time. Just so you know. Hope you're doing well.
Well, message received. What an odd way to get a message like that.
Hey, it's 2021. You got to do what you got to do. You know what I mean?
True.
Yeah,
that's true. So, all right, in the title for this, I pluralize this. We're talking about LSTMs, transformers, and other things that are more than meets the eye. I quite like the pun. Thank you very much. But apparently, LSTM shouldn't even be plural. It's not even entirely sure what it stands for. But
let's get into it.
Well, let's get into it. We're looking at this guy, Leo the Lion Dirac. Paul Dirac's little cousin, I assume. I don't know, actually. Maybe. Tell me how LSTM models for NLP have been practically replaced by transformer-based models. Basic background on NLP and a brief history of supervised learning techniques on documents from bag of words through vanilla and ends. I don't know about you, but whenever I go and I go for vanilla with the chocolate jimmies. So I think that's what this talk is going to be. The vanilla with chocolate. I call them jimmies. I'm not a big sprinkles guy. But so someone literally right before the show started said I was literally up last night working on an article on LSTMs. That was what Aaliyah sent me. And Aaliyah had a show right before mine. And this talk is called LSTM is Dead. Long live Transformers. So
let's go.
Yeah, I don't know if
Seattle Applied Deep Learning. Sad. How sad.
Or saddle, maybe.
Saddle.
Okay. Is it full screen for you now? Are you happy?
More or less.
Okay. As long as you're happy. Yeah.
I didn't say I was happy, but more or less.
Okay.
Let's go.
Let's see what this guy's talking about. Let's see. Let me know if you can hear it too.
All right.
Yeah.
Cool. Well, thanks everybody. So I'm going to give the second talk tonight, which I'm not crazy about, and I don't want this pattern to repeat. But Andrew and I wanted to kick this series off, and
all right. So I'm giving a talk again. I'm not crazy about it, but
yeah,
someone's got to do it, I guess.
I see it's a 30-minute long video. He's like 30 minutes later.
Yeah. What's better than having one talk? Yeah, that's a mood.
What is that in the bottom left? It looks like some kind of logic gate, but I honestly don't know what that is.
Yeah, it looks like a logic gate to me too. I mean,
that's
got
weird.
A tan function in there. We have a circle with a line through it. Yeah, and the bottom.
I mean,
left
it is a logic gate. I'm just not.
What about this thing over here? Let's see. We got a looks like a Corvette.
That's it. Yeah, I wonder what that is.
Yeah, it looks pretty technical there too.
Something's up with that one though. There's more than meets the eye on that one. I don't really know. Something strange about that car. I don't know.
That's what I hope this talk is about. I want to learn
about
that
it.
thing.
Oh, it's an LSTM cell. In the chat.
Oh, okay. Oh, dude, I forgot we even had a chat.
Let's get
Okay, let me
into
get the chat up. Let's get into it. Let's get
And
into
it felt like me talking twice is better than not. But we're gonna get more diversity of folks. If any of you want to give a talk yourselves or know somebody who you think might,
Yeah, I'll give it a
that'd
talk.
be awesome. But a topic that I feel is important for practitioners to understand is a real sea change in natural language processing that's all of like 12 months old, but is one of these things I think is incredibly significant in the field, and that is the advance of the transformers.
This guy's got the shirt tucked in.
So the outline.
Yeah, he does have the shirt.
I wonder sometimes if I should go for the tucked look. You know what I mean?
I think about that a lot too.
I don't know if it's coming back yet, though.
Does he have shorts on too? Does he have a shirt tucked into shorts?
No, those are full long khakis he's got going.
So he's ready for like an adventure. Yeah.
Yeah, man.
That's why they call him Leo the Lion.
I trust this guy already.
I think he's going to give us something good. So he's going to go over NLP, sequence modeling, LSTM, awesome, but not good enough. And then transformers, how and why. That tells you all you need to know, really.
The model is like what determines the effectiveness of the thing. You know what I mean? In machine learning. So whatever model, I don't even know what an LSTM is. That was an LSTM. What was it? A cell of an LSTM? I'm not really sure what that means yet, but
I guess we'll figure it out.
Using a new model is a big deal because usually a lot of the machine learning papers are additions to or testing out different limits of one model, like one popular model that a lot of people will use because it works. If it works at all, if it shows any kind of improvement from a previous model, people will stick to it for a while, and then in my understanding, yeah. So I'm not too much about natural language processing side of machine learning, but yeah. Anyway, apparently this LSTM model was outdated, and
I mean, how hard can it be if babies can figure it out? I'm sure probably easy.
Probably.
Let's see what happens.
For this talk is to start out with some background on natural language processing and
self-plug. Eva Magic's LSTM model article will be out tonight. I can't wait to read it.
Sequence modeling, and then talk about the LSTM, why it's awesome and amazing, but still not good enough, and then go into transformers and talk about how they work and why they're amazing.
I'm ready.
So for background on natural language processing, NLP, I'm going to be talking just about a subset of NLP, which is the supervised learning part of it.
Whoa. You see this math going on? What's going on here?
Not a whole lot.
Let's see here. Okay, so we have f of x. So we have a model, and we have an input into the model, and then we get a prediction. Okay. I think that makes sense.
Well, it kind of equals the prediction. It's.
Let me ask you.
Yeah.
The equal sign with
approximately y.
The suave equal sign. Is that what that means?
It means it's approximately y. Yeah.
Okay, I thought it was just being
exactly
flashy. Okay. So
nope,
not
that's
exactly.
not for style points. But yeah, that's a good analogy though. That f is the function. So a new model would be g of x, for instance. What exactly f is in this case? That's what he's about to explain. So, the input is specific to the problem. So if you're classifying objects, usually there's a standard library of input for machine learning, like for classifier machine learning projects. Usually there's a standard library they use, and then they test the accuracy with that standard library. So it'll be the same images or the same passages for a word-based one or whatever.
Okay.
And yeah, that's the way they can keep it consistent. Because if you keep throwing a bunch of different images at it, you can't really keep a consistent metric of which models, so functions in this case, performed better than others, unless you have the same input. So
the input, whatever we're inputting, is kind of what we want to get a prediction with. Like we want to, like if we're putting in a bunch of numbers, we want to make a prediction of a number.
So in natural language processing, the input would be, I don't know, 60 pages of text, but a lot of people will use the same 60 pages of text just to keep it consistent. So you can say, I've got my model here. You've got your model there. We're both going to use the same input, and mine is going to be better than yours or worse than yours. And that way we'll know, because F is what they're really trying to get. F is all they care about, the input. There's a million different possible inputs for this application, particularly for classifying things. So F is what they research and what they develop. You know, the outcome prediction is just how they measure the effectiveness of F, because they know what it is. They know what it. They know it's a flower or whatever. They know what the text is about. NLP, for instance, is gonna. One of the things I saw in the JPEG for the thing for the video is it's gonna summarize a piece of text and determine whether or not it's spam, right? Mm-hmm. So the input here would be a bunch of spam text, a bunch of regular text, a bunch of advertisement, whatever. But it's going to be the same stuff as other instances of research, right? And people are going to try out different models, so F or G or T or whatever, common function names. And the prediction will be whether or not it is spam or whether or not it's an advertisement or whatever. And, you know, since they'll know the actual answer to all that stuff, they'll measure the different functions against that, or they'll measure the percentage at which the function correctly predicted whether or not something was spam, or whether or not something was an advertisement, or whether or not something was a critical piece of something, or whatever, criticized somebody or whatever, or supported somebody. But yeah, anyway, go ahead.
Well, that makes sense to me, everything that you said. And in fact, I think, like, when I looked at this, I thought I was just going to blow by it, but no, I think it's really important to understand. I think the base case sort of thing of what exactly is going on here, because you could sum up like all of machine learning kind of with this equation, wouldn't you think? It's just
more or less that I know about. Yeah, more.
I know about too.
This is the basics of it. Is you know, it's always a prediction. It's never, you know, it's always a percentage. They go with the highest percentage thing is that it's a flower, or that it's about, you know, the Sixers or whatever. It's always a guess.
Makes sense.
Yeah.
All right, let's keep moving.
So not structured prediction, not sequence prediction, but where you're taking a document as some input and trying to predict some fairly straightforward output about it, like, is this document spam? Right? And
yes.
So what this means is that you need to somehow take your document and represent it as a.
What are you thinking?
So this is like your when you do something like this, you're mapping, that arrow is a map. So that R is the rational numbers. I don't know what D is in this case, I have to admit, but it's probably the length of something, the length of the document or something like that. But F, what this is saying is that F maps R to the D to R. So I believe your output is a rational number, most likely a prediction tied to a particular you know, classification, whether or not it's spam or whatever.
Right.
So, I don't. He's gonna say what D is, though. I don't know what that is.
Let's find out what D is. Maybe D is document size.
Fixed size vector. Could be. Because I'm aware of any linear algebra that works on vectors of variable dimensionality. And the challenge with this is that documents are of variable length. Right? So you have to come up with some way of taking that document and meaningfully encoding it into a fixed size vector, right?
Oh, so okay. I think he was taking that D and just using that as a variable. And then what we're going to do is we're going to take that fixed size vector and just map it to something.
Yeah.
That way we have something that's a fixed size.
In order to use linear algebra on it, it has to become a fixed size vector.
Yeah. All right, bag of words. That's a meal at Moe's, I believe.
This is the bag of words.
Yeah. Okay.
Right, where you have one dimension.
Okay, there you go. It's a dimension.
Okay. So English has, I don't know, about 100,000 words in the vocabulary.
I wonder what dimension means exactly.
So you have a 100,000 dimensional vector. Most of them are 0 because most words are not present.
Vector, I think. So
interesting. Interesting. Yeah.
Like, part of me wants to like, if you don't know linear algebra, this is what a vector looks like. But like, honestly, it probably wouldn't make anything that much clearer if I told you. Well, for the computer science people, it might actually. So like, you know, linear algebra, just to see it, because it's an array. It looks like an array.
Yeah.
Oh, is it going to give me a whole bunch of different things that I don't really care about? Oh, yeah, it like looks like this.
We can't see it.
No, you can't see it.
You're
Okay.
full screen on the thing. That's
it's an array. So Google array. I don't know what to tell you. All right, let's keep going.
In your document, and the ones that are have some value that's maybe a count or TF-IDF score or something like that.
TF-IDF score. I don't know what that is.
That is your vector.
That too.
And this naturally leads to sparse data,
important.
where again it's mostly zeros. You don't store the zeros because that's computationally inefficient. You store lists of position value tuples, or maybe just a list of positions.
Is this boring you, Chris?
I have to say, no. I mean, I'm looking at that. That's a strange way to write that, but yeah, int value tuples of. So I don't. When he says don't store the zeros, I'm not sure what he means by that. The words that are not used, like.
Oh,
yeah,
maybe.
I don't know, because obviously you only have so much memory. You don't want to store all the words in the English language. That's probably a common problem they run into, is to store every word in the English language. It's gonna, for your Python file, it's gonna take up like all your memory. There's so many words that to store them in any kind of data structure like a list or anything like that, it's going to be a nightmare memory-wise. Yeah, so he's saying. So what is he saying then? Like, what? How do they even determine? So that they just store the words that are in the document. Yeah.
Right. It wouldn't make sense to store 0 in that sense, like to store that a word's not in the document. That makes sense.
Yeah. I'm not sure what he means by position, though.
I
don't know.
And this makes the computation much cheaper. And this works. This works reasonably well. Key limitation is that when you're looking at an actual document, order matters, right? These two documents mean completely different things.
Yeah, that's tricky.
Right? But a bag of words model will score them identically every single time because they have the exact same vectors for what words are present. So the solution to that in this context is n-grams. You can have bigrams, which are every pair of possible words, or trigrams, which are every combination of 3 words, which would easily distinguish between those two.
No, that'd be insane. Yeah, that'd be insane.
Quadrillion dimensional.
Yeah, that would be.
You can do it, but you start running into all sorts of problems.
You run out of memory
doing that. Walk down that path.
Yeah.
Wouldn't even be close.
So in neural network land, the natural way to solve this problem is the RNN, which is the recurrent neural network, not the recursive neural network. I've made that mistake.
Recurrent neural network. If I can walk away with that, I'll be happy. Recurrent neural network. And I've watched a YouTube video on RNNs before, so you could say I'm a little bit of an expert on this. Feeling pretty good about it.
I don't know what it means, genius. So
you know what?
Why don't you go ahead and fill this all in, Brian?
Yeah, well, it's a neural network that has very short-term memory, essentially. It's really fast, though. It's like Dory. I think he shows a picture of Dory. If it wasn't this video, it was another one. No, it's another one.
Gotcha.
And then they'll tell us.
But RNNs are a new approach to this, which
that's what I was saying.
How do you calculate a function on a variable length set of input? And they answer it using a for loop in math,
where
they recursively define.
They recursively define. Okay.
Yeah. What is that? A recurrence relation is what that's called. Yeah.
I've never seen this.
This is the same thing as the Fibonacci code or sequence. You know what that is?
Yeah, 1 plus 2.
If this were the Fibonacci sequence, that h would be, or it would say h of I plus 1 equals h of I plus h of I minus 1. Right? So I don't know what the a function is here. The operator here is, it's, h I plus 1 equals addition, I'm going to guess. That's actually what the Fibonacci sequence would be, except I don't know what x would be in this case. Go ahead. Just let it talk.
Output at any stage as a function of the inputs at the previous stages in the previous output. And then for the purpose of supervised learning, the final output is just the final hidden state here. Right? And so visually, this looks like this activation, which takes an input from document X and also itself in the previous time. And you can unroll this and visualize it as a very deep neural network. where the final answer, the number you're looking at the end is this, and it's this deep neural network that processes every one of the inputs along the way.
Okay, hold on. So what's going on here, I think, is that we start at like x0, which is our initial neural network state. That's like its initial state. And then when we go to the next thing, when we go to x1, we have the hidden state 1. We have h1 on top of it. And that h1 is like the improvement from h0 that it brings over. And then it goes over to x2. And it's like, all right. So that's kind of what I think is going on all the way up for x of t or h of t or whatever. I think that's what we're looking at. Does that make sense to you?
Yeah, no, I mean, well, the activation function is what gets you to you know, more and more higher levels of the hidden state end of x. So yeah.
Okay. So I think we're good.
That's what the recurrence relation said too. Is that h of I plus 1 equals the activation of h of I and x of I. So,
dude,
yeah,
freaking killing it right now. This is really good. All right, let's keep going.
Yeah.
Right, and the problem with this classic vanilla RNN, this plain recurrent neural network, is vanishing and exploding gradients. Right, so you take this recursive definition of the hidden state, and you imagine what happens just 3 points in, right? And so you're calling this A function, this A transformation, over and over and over again on your data. And classically in the vanilla case, this is just some matrix multiplication, some learned matrix W times your input X. And so when you go out and say 100 words in, you're taking that W matrix and you're multiplying it 100 times. Right, so
let me ask you this code with the equal sign. What's that about?
I believe that's an assignment, or I believe that's an assignment in pseudocode. So like it's saying that I don't know. It's saying that h of x is assigned to this value. I could be wrong about that. I'm not really sure. But
I think that's pretty, because we're talking about vanishing and exploding gradients, and I know with RNN one of the things is like your gradients, because you know these guys, they can't help but start multiplying stuff and you know going crazy. So
could you go back a little bit when he's talking about the W? He said he described
I missed the W as well. Yeah, so let's see here.
Definition of the hidden state, and you imagine what happens just.
You have to go back that far, Brian. But all right.
So you're calling this A function, this A transformation, over and over and over again.
I mean, right now we've seen this.
And classically in the vanilla case.
What was that? You want me to go back farther?
No, we're good. We're good.
Oh, okay.
Just let it go.
This is just some matrix multiplication, some learned matrix W times your input X.
Learned matrix W times some input X.
Learned matrix W.
Learned matrix W times some input X. Okay, so the learned matrix W and then plus Z of H. H being the hidden state, Z being the change in the hidden state?
I don't know. I don't know. I don't know. I don't know about
when
Z.
You go out and say 100 words.
Yeah. So when you go out, say 100 words. Let's see.
You're taking that W matrix and you're multiplying it 100 times, right? So in simple math, in real number math,
let's see the simple math.
Any number less than 1 and raise it to a very high dimensional value, very high exponent, you get some incredibly small number. And if your number is slightly larger than 1, then it blows up to something large number. And if your exponent's even higher, if you have longer documents, this gets even worse. And in linear algebra, this is about the same, except you need to think about the eigenvalues of
eigenvalues.
Eigenvalues say how much the matrix is going to grow or shrink vectors when the transformation is applied. And if your eigenvalues are less than 1 in this transformation, you're going to get these gradients that go to 0 as you use this matrix over and over again. If they're greater than 1, then your gradients are going to explode. Right? So this made vanilla RNN extremely difficult to work on. Basically just didn't work on.
So your changes get smaller and smaller or bigger and bigger the more you kind of back propagate, I guess, is what.
Well, it's with each iteration, it grows so much if your whatever value is above 1. If it's below 1, it shrinks so small that I don't know why having an extremely small matrix or W value would impede you. I would think that would be better practically. I'm not really sure how that would reflect in memory, but obviously, if your matrix is, every time you multiply two matrices that are of the same, if they're of the same dimensions, I believe the product is of the same dimensions, right?
I think so. That sounds right to me.
I believe that's the case.
Yeah, because you would have.
It's been a long time since I've done that stuff, but regardless,
I feel good about it. Yeah,
it may increase in dimension. Let me just look that up real quick.
I thought it was something like if you have, like if I wanted to go from 3-dimensional to 4-dimensional, at least one of my vectors would have to be 4-dimensional, right?
Yeah.
And then I apply the transformation on it.
4-dimensional.
I don't know. Very suspicious. I'm not sure.
Yeah, I think so. If you multiply two matrices with the same dimensions, I believe the product is the same dimensions or has the same dimensions, but I don't know. The values inside would obviously be getting either insanely small or insanely large, depending on whether or not it's below or above 1. So apparently that doesn't work. That's no good. After a certain period of time, that's unusable for what he's saying.
And basically just didn't work on anything is what he's saying. Yeah. Okay. Cool.
Anything but fairly short sequences. Right. So
you need fairly short sequences, otherwise your gradient explodes. That's what it's all about. Okay.
That was the problem. That was the problem before LSTM.
That was the problem with RNN. So now let's get LSTMs to the rescue before we learn about how they suck too.
LSTM to the rescue.
Yeah.
Right.
And why they need to go.
I wrote this document a few years ago called "The Rise and Fall of LSTM." So LSTM.
So at least Tim.
At least Tim came. All right.
I like that way more. Let's go to the at least Tim came rescue.
Came around in the Dark Ages, and then it went into the AI winter. It came back again for a while, but I think it's on its way out again now with transformers.
AI winter.
So LSTM, to be clear, is a kind of recurrent neural network. It just has a more sophisticated cell inside. And it was invented originally in the Dark Ages on this stone tablet that has been recovered into a PDF that you can access on Sepp Hochreiter's server.
So he's joking.
I kid, and you're
he said I kid.
Them quite a bit. But they
Joel.
did a bunch of amazing work in the 90s that was really well.
You got us again.
Leo had that one ready.
Neglected, forgotten. As time goes on.
Yeah, instead of just showing the paper, it'd be cool if I had it fade in from like an old stone tablet, and I'll make a stone tablet joke.
Yeah, no, that'd be great. Alicia, get on that. Take care of that. Yeah.
That's totally not fair because they did amazing research. Yeah. So the LSTM cell looks like this.
There it is.
2 hidden states.
There we go.
And the
2 hidden
input coming along the
states.
bottom, and the output up the top again. And these 2 hidden states. And I'm not going to go into it in detail, and you should totally look at Christopher Ola's blog post if you want to dive into it. But the
you know
key
what?
point
I don't think
is
so.
that these transformations, these are the matrix multiplies, right? And they are not applied recursively on the main hidden vector. All you're doing is you're adding in, or the forget gate, you actually don't really need it. But you're adding in some new number. And so the LSTM is actually a lot like a ResNet. It's a lot like a CNN ResNet in that you're adding new values onto the activation as you go through.
I don't remember, but I've heard of it before.
Right, and so this solves the exploding and vanishing gradients problems.
Okay.
However, LSTM is still pretty difficult to train because you still have these very long gradient paths. Even with those residual connections, you're still propagating gradients from the end all the way through this transformation cell over to the beginning. And for a long document, this means very, very deep networks that are notoriously difficult to train. And more importantly, transfer learning never really worked on these LSTM models.
Well, that's
right?
lame.
One of the great things about ImageNet and CNNs is that you can train a convolutional net on millions of images in ImageNet and take that neural network and fine-tune it for some new problem that you have. And the starting state of the ImageNet CNN gives you a great place to start from when you're looking for a new neural network, and makes training on your own problem much easier with much less data. That never really worked with LSTM. Sometimes it did, but
With
it wasn't very reliable.
LSTM.
Which means that anytime you're using an LSTM, you need a new labeled data set that's specific to your task.
Okay.
And that's expensive.
Yeah.
Okay, so this changed dramatically.
So in case someone's watching and they're wondering what transfer learning is, it's just that I can use my model on like something else other than the thing I originally built it for. And LSTMs can't do that, I guess.
Nope.
Because its networks are very specific to whatever it is you gave it.
Yeah. It needs a specific labeled data set for every task. So
sounds like
you can't just plug in whatever data set you want to test it out, to test out your model. It has to have a specific one that like each time each of its tasks are tailored to work with one specific data. They're basically hard coded to work with one specific data set.
That makes sense to me. So
it's not adaptable.
If we wanted like hyper transferability, then we would use a CNN and just expect that like we're not going to have very long-term memory. So it'll be all right for some stuff, but for other stuff it won't work. LSTMs will be great for other stuff, but you're going to use it on that one thing, and I hope you are okay with that.
Yeah.
I'm Gucci. Okay. I'm you know what? I don't feel out of depth here. I feel fine.
Yeah. Okay.
Famous last words.
Dramatically, just about a year ago, when the BERT model was
Here we go.
Was released.
Now this I understand.
So you'll hear people talk about transformers and Muppets together, and the reason for this is that
how'd they get that picture of us
on this?
Yeah, now they're talking my language.
Architecture was called the Transformer Network. And then the BERT paper is a Muppet, and there's an Elmo paper, and researchers just run with the joke. So this is just context. You understand what people are talking about if they say, "We'll use a Muppet network." Right, what the heck are you talking about? A Muppet network? So this, I think of as the natural progression of this sequence of document models, and the transformer model was first described about 2.5 years ago in this paper, "Attention is All You Need," and this paper was addressing machine translation. So think about taking a document in English and converting it into French, right? And so the classic way to do this,
Nikki Palmer is up to these days.
Here's the full structure. There's a lot going on here, right?
Yeah,
so it's not LSTM.
On the encoding, that's all you need for these supervised learning problems.
It's kind of insane.
Similar anyway.
Yeah.
So
it's too much. I don't care about it. Okay,
it's too much right now.
So but basically, there's 3 parts. We're going to talk about, first we're going to talk about this attention part, then we'll talk about the part of the bottom of the positional encoding. The top part's just not that hard. It's just a simple, fully connected layer. So the attention mechanism in the middle is the key to making this thing work on documents of variable length.
Trying to figure out.
The way to do that is by having an
Thank God.
comparison. For every layer of the neural network, it considers for every output of the next layer, considers every possible input from the previous layer in this n-squared way. And it does this weighted sum of the previous ones, where the weighting is the learned function, right? And then it applies just a fully connected layer after it. But this is great for a number of reasons. One is that you can look at this thing and you can visually see what it's doing. So here is this translation problem of converting from the English sentence. The agreement on the European Economic Area was signed in August 1992. And to translate that into French, my apologies, l'accord sur la zone économique européenne a été signé en août. I forgot.
I like that he said apologies in advance as if he was going to butcher the French language, and then he just comes out with that fluent French. Yeah, I kind of don't like that. He knows he speaks French.
Yeah, he shouldn't have apologized. Yeah.
He knew he says it perfectly. Was someone going to correct him? Actually, Leo.
Actually, excuse me. Don't want to hold up the presentation, but I must say.
Yeah. Great talk and all, but when you were talking French,
you just lost me.
Yeah,
totally. I was following everything until that point.
Cringe, bro.
Moving. Yeah.
Yeah. I don't know who gave you the right.
Cringe, bro. Yeah. Okay. Well, this is interesting though. What do you think that? So those the shade the what is it? I guess the how dark the thing is or how light the thing is how confident it is that that's the word. So you can see for economique, it is sort of thinking maybe that's European.
You didn't apologize before you tried to...
I'm sorry. Before I say this, economique, it thinks that might maybe be European. You know what I'm saying? Or
right.
It thinks that economic, probably because of the two O's, or no, not the O and the N.
Yeah.
Actually, yeah. Two O's and an N.
There's an E, there's an O.
It might think that that's zone, just based on letters alone, or a word related to zone, like zoning.
It's like playing Wheel of Fortune over there.
Yeah. What about, what I don't get is why it would think that A or is related to the word signed.
Yeah. I don't know. It's having a hard time with that letter A.
Yeah, it is crossing languages. It's not. Yeah. So there's some other criteria for which these predictions are made.
Not even an A in signed. That's what's weird.
It's saying that signed. It's a little bit thinking that signed might mean agreement, or the French word of sign. Like you see how it's a little bit later with the agreement there. Yeah. So it's probably just the word signed usually accompanies the word agreement, or that's usually where you would see it. Something along those lines. I don't know. I'm not sure. But this is interesting, though, that you can see the different predictions it makes and how confident it is. So zone, it's not super confident. With European, it's as confident as it gets. It's just, opaque.
100%. I know this word.
Zone is much, much less confident because it shares only one letter with area, and it's not used in the same position or anything. It's the same length as area. Maybe that has something to do with it. But yeah. Anyway, this is cool.
Yeah, let's keep going.
1992. Right, and you can see the attention. So as it's generating, each token in the output, it's starting with this whole thing as the input, and it's generating these output tokens one at a time, and it says, okay, first I got to translate the. The way I do that, it translates into la, and all I'm doing is looking at this. Next, I output accord. All I'm doing is looking at agreement. Then sur is on, la is the. Okay, now, interesting. European Economic Area translates into Zone Économique Européenne. So the order is reversed, right? And you can see the attention mechanism is reversed also.
Yeah, look at that.
Very clearly what this thing
would you look at that?
It's running along.
Yeah.
And the way it works in
Makes
the attention, the transformer model, the way they describe it, is with query and key vectors. So for every output position, you generate a query, and for every input that you're considering, you generate a key, and then the relevance score is just the dot product of those two. Right, and to visualize that, you first
I won't spend too much time there.
The query and the key values,
with them.
And that gives you the relevance scores. You use a softmax to normalize them, and then you do a weighted average of the values, the third version of each token, to get your output. Now, to explain this in a little bit more detail, I'm going to go through it in pseudocode. So this looks like Python. It wouldn't actually run, but I think it's close enough to help people understand what's going on. So you've got this attention
doesn't look that hard.
Function, right? And it takes as input a list of tensors. I know you don't need to do that. A list of tensors, one per.
What's a tensor?
I'm not sure.
Let me look it up. Let me just look it up. I'm going to look it up. Tensor. What is a tensor?
I use TensorFlow for machine learning stuff, but I don't know what tensor actually means.
Yeah. Okay, a tensor. Hold on. If I could just see an image of it. Okay, if you could see the image I'm looking at, you can't. But
I'm trying to visualize it.
Type in what is a tensor, and then look at the second image, and then it looks like an array of like other matrices. Matrix.
Yeah, no, it's what it is. It's a matrix of submatrices.
Oh, I guess we need a whole new word for that.
That makes sense.
These math.
Well,
people.
yeah, no, matrix within a matrix. Yeah.
So in our list, X in list tensor. So a list of matrices, a list of matrices.
Yep. Well, a matrix of matrices.
A list of a matrix of matrices.
It's a matrix.
Okay.
So what it takes is, yes, a list of matrices of matrices. Yeah.
And then the query I value. Huh.
Token on the input.
Self.q.
And then the first thing it does, it goes through everything in the sequence, and it computes the query, the key, and the value.
Self.q being self.query, I guess, like shorthand, self.key, self.value times the transformation. For every token, transform previous layers out. Okay.
So it's that thing we saw in the beginning where any token you get in a list is the product of using some kind of activation function on the previous token.
Right.
So
okay. I see.
So you're just continuously, recursively activating it, everything in the list. So the last element in the list is an element that is derived from. Say the list is length 10. The activation function was called, I believe, 9 times. Yeah, it's n minus 1. It's the length of the list minus 1. That's how many times the activation function was called recursively. Beginning with the base case is the first, h sub 0 of that list of that recursive sequence. Yeah, good.
Makes sense to me.
Yeah.
Matrices, right? So it learns this transformation from the previous layer to whatever should be the query, the key, and the value at the next layer. Then it goes through this double nested loop, right? So for every output token, it figures out, okay, this is the query I'm working with, and then it goes through everything in the input, and it multiplies that query with the key from the possible key, and it computes a whole bunch of relevant scores, and then it normalizes these relevant scores using a softmax, which makes sure that they just all add up to 1. So you can sensibly use that to compute a weighted sum of all of the values. So now you just go through, for each output, you go through each of the input tokens, the value score, which is calculated for them, and you multiply it by the relevance. This is just a floating point number from 0 to 1. And you get a weighted average, which is the output, and you return that. So this is what's going on in the attention mechanism, which can be pretty confusing when you just look at a diagram like that. But I hope this explains it a little bit.
Yeah, I feel like I'd really have to play with this and probably, see it in action. But it makes sense
to learn if you the big diagram. Okay, so the thing that he has on the bottom left there, the full diagram version of that. I feel like if you understand every component of that, you'll actually understand this entire thing. Like I guess he's talking about the thing that they're replacing. That's being replaced. That's irrelevant now.
Right.
So
right.
You'll understand why its shortcomings were surpassed by the newer by Transformers. Yeah. So LSTM is dead. Okay.
Yeah, this sucks.
Yeah.
You can see what the Transformers are all about.
So relevant scores are interpretable, as I say, and this is super helpful, right? Now an innovation, I think it was novel in the Transformer paper, is multi-headed attention. And this is one of these really clever and important innovations that it's not actually all that complicated at all.
No, good.
You just do that same thing, that same attention mechanism 8 times.
8 times.
Whatever value of 8 you want to use. And that lets the network learn 8 different things to pay attention to. So in the translation case, it can learn an attention mechanism for grammar, one for vocabulary, one for gender, one for tense, whatever it is, right? Whatever the thing needs to, it can look at different parts of the input document for different purposes and do this at each layer.
That's pretty
right?
cool.
So you can kind of intuitively see how this would be a really flexible mechanism for processing a document or any sequence. Okay, so that is one of the key things that enables the transformer model. That's the multi-headed attention part of it. Now let's look down here at the positional encoding, which is critical and novel and critical innovation that I think is incredibly clever. So without this positional encoding, attention mechanisms are just bags of words, right? There's nothing saying what the difference is between
we got some graphs
work
soon.
to live or live to work.
Okay,
right?
we get to why transformers are awesome pretty quick.
They're all equivalent positions, and you're just going to compute some score for each of them. So what they did is they took a lesson from Fourier theory and added in a bunch of sines and cosines as extra dimensions. Sorry, not as extra dimensions, but onto the word embeddings. So going back. So what they do is they take the inputs, they use word to vec to calculate some vector for each input token, and then onto that embedding, they add a bunch of sine and cosines of different frequencies, starting at just pi and then stretching out longer and longer and longer.
Oh, cool.
If you look at the whole thing, it looks like this. And what this does is it lets the model reason about the relative position of any tokens. Right? So if you can kind of imagine that the model can say if the orange dimension is slightly higher than the blue dimension on one word versus another, then you can see how it knows that that token is to the left or right of the other. And because it has this at all these different wavelengths, it can look across the entire document at kind of arbitrary scales to see whether one idea is before or after another. The key thing is that this is how the system understands position and isn't just a bag of words when doing the attention. So transformers, those are the two key innovations, is positional encoding and multi-headed attention. Transformers are awesome, even though they're n squared in the length of the document. These all-to-all comparisons can be done almost for free in a modern GPU. GPUs change all sorts of things, right? You can do a 1,000 by 1,000 matrix multiply as fast as you can do a 10 by 10 in a lot of cases, because they have so much parallelism, they have so much bandwidth, that, but a fixed latency for every operation. So you can do these massive, massive multiplies almost for free in a lot of cases. So doing things in n squared is not actually necessarily much more expensive. Whereas in an RNN, like an LSTM, you can't.
Is that why AMD to the moon soon?
AMD GPUs are not.
Not good at this.
I don't know. I mean, I'm sure they'd be. It depends on how many cores they have.
Yeah, be
what
careful.
He's saying is that
Dubé fanboys will be after you.
You know how Bitcoin, they mine it with GPUs. That's because it has so many cores and they require parallel, operations. They need to compute several things at once on the same GPU. They need to distribute as many sub operations as they possibly can. GPUs can have, I don't know, I actually don't know the figure, but it's way, way more cores than a CPU. They have so many cores in there. Modern GPUs, at least. That's that's what he's saying, is that regardless, because you can parallelize all that stuff, like for an n squared operation, the actual time you measure between a linear operation, O of n, or a quadratic one, O of n squared, is going to be basically the same, because you're doing all those extra steps at the same time as the, for a 1,000 by 1,000 matrix, you're multiplying multiple rows at once. You know what I'm saying?
Right.
Instead of going one by one by one by one, you're doing that for 10 rows at once, 50 rows at once, 100 rows at one time, depending on how many cores you have and how many, subcores they have. Each one can handle one or more of those rows at once.
So since we can do that, I guess we might as well use transformers to do these parallel operations. Whereas RNNs and LSTMs have to be computed in serial per token, so I guess in a sequence. Yeah, pretty much. Everything has to be computed sequentially. So you gotta sit there and wait for that.
Yeah, basically, transformers allow you to parallel program this.
I don't have time
which is always a huge benefit. See, GPUs and CPUs back in the day had like 1 or 2 cores. Like parallel programming wasn't possible, really. I don't even know when exactly that happened, but nowadays, certain objects you have to be able to distribute the input amongst parallel processes. Like there's some problems where you can't do that. Like for instance, if you're generating permutations of a list, right? Say you have 1, 2, 3, and you need 1, 3, 2, 3, 1, 2, 3, 2, 1, etc.
In that order.
There are the size of the list factorial possible permutations. So in this case, if the length is 3, there are 6 permutations, right? You can't parallelize that, to my knowledge. You can't get multiple cores to compute 2 permutations each or something like that, because they can't check while they're doing it to see what the other core is doing.
Yeah,
like it's its own operation. It's like you're running it on a separate CPU. So as far as I know, I mean, there's probably a way to manage that, but there's different multi-threading algorithms and stuff like that. But regardless, yeah, if that's all I can take away from this video is that transformers allow you to parallelize machine learning operations, which are extremely costly, especially with language stuff. Then yeah, that's huge. I don't know why you couldn't parallelize stuff with an LSTM. I guess it all had to be in the same, like, logic gate type thing.
The same cell.
Whatever it is, you can't do it. It has to be computed serially. So yeah, anyway.
That's why there's more than meets the eye. Let's keep going until we hit to 8 o'clock, and then I'll leave the rest for the people at home to finish up, because I think the last is like a Q&A or something. No one ever stays for Q&A.
Anything with Topical 11 until you're completely done.
Imagine non-ironically doing Q&A.
Imagine not leaving
much more computationally efficient. Also, you don't need to use.
Imagine not showing up late and loudly sitting in your seat,
taking a couple calls with your ringer at full volume, asking them to hold on a second. Like I gotta take this, everybody. Just relax.
Immediately get a call as soon as you walk in late.
Oh hey, no, I'm not doing anything important right now. Yeah, no, go ahead, speak up.
No, it's just some schmuck talking right now. Huh? What was that?
Well, this guy knows his stuff, man. For somebody who doesn't like to do presentations, he knows his stuff. Do you know what the symbol is? The bottom left arrow that's going up, right?
Bottom left arrow.
So there's 3 symbols there. It's the symbol, the tan H, then the symbol. What is that symbol? I've seen it before. I just don't know what it is.
The circle.
Is that little omega? I don't think it is. No.
It looks like variance to me. It looks like the symbol for like variance or variance symbol. Let me look it up. I wish you could see it too. Yeah, it's the symbol for variance.
I'm not really sure what it means in this context.
Or like standard deviation sort of thing.
Okay, that makes sense.
It's the population standard deviation.
The sigmoid function, is that what it is?
Sigmoid is sigmoid function. I think the sigmoid function, because he does talk about sigmoid is I think this little o is just talking about like whatever the changes in whatever are variable, like after it's gone through, we make a change. And that change is done by the neural network, and then it runs through the tan function, and then the tan function puts it between 1 and -1, and then and the variance just has to do with the variance of the data. I think. I don't know. And I don't know. Maybe
we might find out right now.
Let's see. Let's see if I'm close.
Sigmoid or tan H activation functions, which are built into the LSTM model, these things that scale your activations to 0 or 1. Why are these things problematic? So these were bread and butter in the old days of neural networks. People would use these between layers all the time. And they make sense there. They're kind of biologically inspired. You take any activation, you scale it from 0 to 1 or -1 to 1. But they're actually really, really problematic, because if you get a neuron which has a very high activation value, then you've got this number up here, which is 1, and you take the derivative of that, and it's 0.
Or
it's some very, very small number. And so your gradient descent can't tell the difference between an activation up here and one way over on the other side. So it's very easy for the trainer to get confused if your activations don't stay near this middle part, right? And that's problematic. Compare that to ReLU, which is the standard these days. And ReLU, yes, it does have this very, very large dead space, but if you're not in the dead space, then there's nothing stopping it from getting bigger and bigger and scaling off to infinity. And one of the reasons why one of the
you could have a very
works better, as Jeffrey Hinton puts it,
strong opinion.
Is that this allows each neuron to express a stronger opinion. Right? In in a sigmoid, there is really no difference between the activation being 3 or 8 or 20 or 100. The output is the same. Right? All it can say is kind of yes, no, maybe. Right? But with a ReLU, it can say an activation of 5 or 100 or 1,000, and these are all meaningfully different values that can be used for different purposes down the line, right? So each neuron can express more information. Also, the gradient doesn't saturate. We talked about that. Very critically, and I think this is really underappreciated, ReLUs are really insensitive to random initialization. If you're working with a bunch of sigmoid layers, you need to pick those random values at the beginning of your training to make sure that your activation values are in that middle part where you're going to get reasonable gradients. And people used to worry a lot about what initialization to use for your neural network. You don't hear people...
Good to skip ahead.
If you're designing a new network...
I want to see... Let's get some general deep learning wisdom, and then that'll be... Let's just say.
For whatever reason, don't bother messing with different kinds of activations. Don't bother trying sigmoid or tanh. They're probably not going to work out very well.
I thought we had to do that.
But different optimizers. Atom is...
No, actually, it turns out it's a stupid idea. Don't do that.
Have a bit of a tendency to overfit. If you're trying to squeeze the juice out of your system and you want the best results, STD is likely to get you a better result, but it's going to take...
This thing I saw, I was looking on Stack Exchange earlier to fix this thing. I was trying to generate a random number under certain conditions. I don't remember what it was. And the answer told you how to do it. And then randomly says, don't ever do this. This is the wrong thing to do. You need to fix whatever it is that caused you to need to do this, because this will absolutely break everything. You're not meant to use Python this way or whatever. It's just funny. Like,
yeah,
yeah.
I was doing a recursive, I was doing tail recursion. And they were like, check out this article on tail recursion. And they're like, yeah. So sometimes, your language is pretty good at it, but then other times you have something like Python where it's just an abomination. And that's what I was doing.
Python, it has its issues, but overall, it's very simple and very easy to use. It
ended up being not that hard.
Yeah.
So I don't know what that guy's problem was. Everyone always has a bone to pick with the language or whatever.
Yeah, they do. It's a snobby business, this whole
these people, if you can call them people.
Different activations don't really matter.
Sometimes RMS problem beats the pants off both of them.
Maybe we missed something right before this, but I thought the whole point of what we were doing here was that the activations mattered. Like, didn't he just say, like, what's the point of ReLU, tanh? Why use ReLU instead of tanh if it doesn't matter? I don't know. That's kind of weird.
Yeah.
Maybe I shouldn't have skipped.
I told you about why I think SWA is
I think it's okay.
There's this system called Attitune that my old team at Amazon released, where you don't even need to pick a learning rate. It dynamically calculates the ideal learning rate schedule at every point during training for you. It's kind of magical.
It's kind of cool.
So it's worth playing around with different optimizers, but don't mess with the activation functions.
Okay. I won't.
Let's pop out. Right? There's a bunch of theory, a bunch of math and ideas.
You're not messing with the activation
functions.
Apply
this stuff. No. So if you want to use a transformer, I strongly
don't even think about it. Hey, TensorFlow.
Over to the fine folks at Hugging Face and download the pre-trained model.
That's what it looks like. That's the code. Megatron LM,
pretty cool. Energy into training this. And I've heard a lot of people, low resource languages.
Well, I'll leave the. I think the rest of this is just him talking about different practical applications, like different real transformers and stuff. So I will leave that for you, the audience, to figure out. I'm curious what the comments are on this video. What does the YouTube community think about it? Let's see. Okay. This person, Fernando, this is one of the best deep learning related presentations I've seen in a while. not only introduced transformers, but also gave an overview of NLP strategies, activation functions, best practices, and optimizers. Thank you. Okay. Good to see Adam Driver working on transformers. Yeah.
Good one, Bumsy.
Let's see here. For anyone feeling overwhelmed, that's you, viewer. It is completely reasonable, as this video is just a 28-minute recap for experienced machine learning practitioners like us. And a lot of them are just spamming the top comments with, this is by far the best video. Everything is clear with this simple video and all. Thank you.
Got me right there, Sanjeev.
Sanjeev, he can see through the BS. Let's see here. And then here's the exact comment he's talking about. Ismail, you have been found. Let's see here. Any other good talks here? Any good comments? Where can I find the presentation doc of this talk, amigos? Thanks. You can share. Yeah, I don't know. I don't know where the PowerPoint is. Let's see here. Traditional machine learning guy. This guy was into it before it was cool. Yeah, it seems like everyone really got a lot out of this. I hope you did too, viewer. And I'll put this into the chat for the millions and millions of people watching. There you go.
This is that video there, 2020 machine learning roadmap. It's right there. No, you don't have to go up. It was right there.
Oh, wait. Down?
Down. Oh. It's right there.
Down here? Oh, no. Okay. Right here?
Yeah. It's 2.5 hours long, but it's probably, let's get it rolling. No, it's probably
never mind.
Really, really, really interesting.
Sweet.
It's got a lot of information.
Honestly, you want to take a sneak peek of what I'm thinking about next week? I'm thinking about I was literally just watching it. I hate when I watch a video and then I was thinking about looking at our boy Lex.
To 2020
state of the art deep learning.
Lex. Yeah.
He's going to talk about deep learning celebrations, growth, and limitations, some deep RL frameworks, Megatron, XLNet, Albert, which is exactly what he was just talking about.
Yeah.
Alexa Prize.
Lex is crazy with this stuff, man.
Dude, Lex is a freaking G,
he's so on top of it. He's like he knows all this stuff.
He just knows, dude. And the video's an hour long. I don't know. I might watch it tonight, and then maybe I'll do this video for next week. What do you think? Might be a good idea.
Sounds good. Yeah.
If you want to come back on, I'm sure it would be a good time.
Yeah. We'll let my assistant get back to you on that one. No, but I 100% will. And I'll watch it too. If you want to watch it later, we could just watch it. Bang it
kind of down. Emotions are real if I think they're real, and the law should reflect that. All right. I don't know what these comments are talking about. Best AI presenter on the internet.
It's supposed to be some kind of I don't know.
This
Lex
is
might go. He might go off the rails during this one. Is what I'm saying.
He might
because it wouldn't be the first time.
He might be too based for us mortals. Yeah, well, sure. That's it for Tech Topical. Went 3 minutes over, but I think you'll be okay with that. Thank you all so much for. Oh, dude, did you have a show after this? My bad, dude. I forgot you had to go at 8.
Did you? I don't have anything tonight. No, I'm good.
Oh, okay.
Yeah.
Your assistant didn't tell me, so I just.
No. She's busy.
The assistant's busy.
She's putting together that headstone, for the, explaining the RNNs when the first paper of the RNN. Yeah, she's trying to find the right graphic and all that.
Yeah, trying to find the right thing to plagiarize.
Really important that I get that. Somebody posted was that you that posted that link in the chat?
Yeah, that was me.
Okay. I was gonna say.
That's crazy, dude. Anyway, thank you all for coming to Tech Topical. I will see you all next week. Thank you so much to Chris for coming out, and I will see you all next week. All right, and bye-bye.
See you later.